All right, so for A, we are trying to figure out the population of whatever these creatures are after a certain number of days. What is kind of just the basic generic formula before we start plugging in values that we're going to be working with here? Very good. To the power of x. Very, very nice. In this case, what is our value for r going to be? 0.2. And then what is our value for a? 10. Very good. So this is 10 times 1 plus 0.2. And then what am I actually plugging into x? It's going to be after 20 days. Notice that that is because this is 20% per day. So we would say, well, this is going to be 20 days. And so how many of these sea monkeys do we end up with? 383. Very, very good. Now for our adjusted model, our more refined model, we'll say, rather than looking at this kind of like lump sum 20% increase. This is like we leave and then we come back and we look and, oh, it's gone up by 20%. And now we're doing a little bit of a more refined breakdown and saying, well, really what's happening is that 20% is made up of 4-5% increases kind of throughout the day. And so what we're comparing here with B is a lump sum 20% increase all at once versus 4-5% increases kind of as we go. All right. And so let's kind of readjust. Let's talk about what our new formula is going to be. What is our new R value going to be here? 0.05, very good. So initial value in this case still is going to be 10. We're looking at 1 plus now this 0.05. And now the tricky bit here, I would say, is what power do I have to raise this to? Think of this 0.05 as telling us that we are increasing by 5%. I want to find the number of times that I am increasing by 5%. How many times do I increase by 5% in one day? 4. How many days am I doing this by? 20. And so how many times am I going to increase by 5% overall? That's going to be 80, which is our 4 times the number of days. This is 4 times 20. And what did we see here? It's like 495 of these creatures. Okay, this should feel a little bit weird, hopefully, at first glance. Why on earth would taking this 20% and breaking it up into 4 different iterations, why would that give us a larger value than just taking that 20% all at once at one kind of point during the day? What's going on here? Taking lower percent by a larger number, so they're going to have more. Very, very nice. So this 5% is going to be working on the initial population just like this 20% is, right? But what is this second 5% going to be working on? Well, it's going to be working on the original population, but then also the 5% addition that we saw from that first 5%. What does this third 5% work on? Well, it is still working on that original population, but it is also working on the second 5% increase. It's also working on that initial 5% increase. And so what we say as we go is that each of these successive 5% increases is really adding more and more and more than the previous 5% increase. And so taking this process of increasing by 20% and spreading it out over the day actually results in a larger end product, because each of the times that we are taking 5%, we are taking 5% of a larger and larger and larger number rather than just kind of taking that 20% all at once. Very, very good. Very astute. All right. This is the entire idea, basically, behind compounded interest, which is the specific problem set that we're going to be looking at today is how do we deal with compounded interest. But I think this is kind of a nice example because it shows you, yeah, we have these compounded interest formulas, but the core ideas can apply to any exponential model. This idea of taking a like lump sum percentage and divvying it up throughout multiple parts of the day and getting a larger value based on the number of times I divvy it up. That is going to be something that is very universal. We're going to see it applies very directly to kind of what we were doing yesterday as well, which is kind of cool. And then another thing to note is that if we wanted to see an even more refined version, so for instance, if we went in and we said, well, really what's going on is we're seeing a bunch of like little 1% increases over and over and over again, we would get an even more refined look, an even larger value, because each of the 1% that adds up to make a 5% is going to be getting larger and larger and larger as we go. And so the further we split apart, hopefully we'll kind of end up seeing the further we split apart this percentage, the larger our value gets. All right, why do we care about having a particularly large value? Well, in the case of like observing a fox population, we don't want a particularly large value, we want an accurate value. But in the case of making a lot of money, we want a particularly large value. And so this is kind of our tie-in here to our compound interest. So I'm going to give you the formula. We're going to take a moment to dissect it. It really is going to be the exact same thing that we did with part B, though. It's the exact same formula. And really, it's just a modification on our exponential growth model here. Just a couple of more pieces that we kind of need to define, but it's really this part B model that we already have. Oftentimes, you'll see this written as A of t, where A is just like the amount of money that you have at a particular time or after a certain amount of time. This is going to be equal to P times 1 plus R over N to the power of N times T. Okay, which looks maybe a little bit more complicated, but really we're going to see it's the exact same thing. So first and foremost, this 100 is still here because after I increase the amount in my account, I don't want to lose the original 100%. So exact same reason why we have this 100 here. When my fox population increases by 13%, the remaining 100 or the original 100% aren't just disappearing, they're still there. So this 1 here is still that original 100%. P in this case is often called the principal. But really, that's the same thing as A. It's like our starting amount. So however much is starting out, what happens when T is equal to 0. Our R is going to be our rate per some amount of time. Often this will be like an annual interest rate. Generally speaking, the time frame that you'll be given is a year, but certainly we could envision a weird circumstance in which I give you like a rate per month and we can do the exact same thing. But generally speaking, this is going to be a rate per like years, is what you would more often than not see. N we can think of as the number of compoundings. Per time. So for instance, in my sea monkey display here, we are looking at taking this 20% and divvying it up 4 times a day. Okay, so we apply the first piece of our 20% at one point, we apply the second piece halfway through the day, the third piece 3/4 of the way, and then the fourth piece kind of at the very end of the day. And so in this case, the number of times that we applied a fraction of our total percent would be 4. The number of compoundings in that case would be 4. All right, so taking my 20%, that value of R, splitting it up into 4 equal chunks, and then applying each of those chunks. And then in this case, we say T is obviously just going to be the time. And then something that I really want to draw note to, this value of NT, the logic that we used here was if I am divvying up my percent and applying it, blah, 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 if I apply it 4 times a day for 20 days, I'm looking at the total number of times that I am increasing by 5%. This would be something akin to the total number of compoundings. So for instance, if I am taking some kind of amount, let's just give it a ludicrous number, we'll say like my account is increasing by 10% and it does it by 5% in June and then another 5% in December, and I want to know what's going on after 20 years, then my power that I'm going to raise to the number of times that I've increased my account by 5% would be 2, the number of times that I'm getting paid throughout a year, times 20, the number of total years, and so you would be increasing your account by 40 times over the course. Exact same reason why we saw our sea monkey example, this being raised to the power of 80. We are we're increasing our population by 5% 4 times a day. We are doing that for 20 days. So the R time is going to give you a, like, I mean, it should be in terms of the T time. You just want to make sure your units match. So for instance, if I gave you kind of similar to what we did yesterday, where I gave you like a rate in terms of days, and you needed to interpret that in terms of what would happen like a year later, replacing a year with 365 days, I could ask you something similar. I could say that we're making 3% interest per month, and then ask you what's going on 3 years down the line, and you would just need to take that 3 years and write it as 36 months, and that would be it. So this is just making sure our units that we use for R are consistent with the units that we are using for T. All right. So let's take a look at this. And actually, we've already kind of seen it in action with B here, but let's kind of take a look at this in the context that we would actually most often see it. So looking at example 3, we were trying to use our compound interest formula in order to calculate how much money is going to be in our account after a designated amount of time. The wording on this is a little bit wonky. I would clean this up on like a test or quiz. The 3% that we are talking about here is our yearly interest rate. And this yearly interest rate is being divvied up quarterly. And so we're getting 1/4 of this yearly interest rate at each quarter. So you would get like 0.75% during the first quarter and during the second quarter and so on. All right. So plugging this into our formula here, this is going to be, let's see here. This is going to be A of T equal to, what is the initial amount that we are starting with? We're starting with $1,000. We are keeping that $1,000, so we need that 1 there. And then we are adding on top of it that 3%, that 0.03. But then how much of that 3% kind of at each turn? We want 1/4 of that 3%, because we are going to be seeing that piece of our 3% 4 times. We want to total up to 3%. And then what are we raising this to? Well, that's going to be 4 times a year times the number of years, in this case, T. All right, so how do I find what's going on after 10 years? Well, that's just going to be a simple matter of taking our value for T, subbing this in. So this is 1,000 times 1.0075 to the power of 4 times 10. I get from this, this is going to be round to 2 decimal places since we're talking about money, $1348.35. All right, questions here? Pretty much exactly the same thing that we just did over here, right? We're taking our 3%, we're divvying it up into fourths. And then how often am I going to be increasing my account by that 0.75%? Well, it's going to be 4 times the number of year, 4 times per year, number of years, in this case 10, so 40 times total. You get your total amount in your account. How is this going to change versus when we're looking at doing this quarterly versus weekly? Well, really the only thing that's going to change is instead of divvying this up into fourths, what are we going to be divvying it up by? We're going to be dividing it by 52. And how often will we see our payments per year? How many payments would we expect to get per year? We'd expect to get 52 payments over the course of the year. Very, very kind of small payments, small increases as we go. And what would our prediction be? Is this going to give us more money in our account than when we were doing this quarterly, or less money in our account than when we were doing this quarterly? We'd expect more, because each of the kind of tiny slivers that's getting added into our account is then getting acted on by each kind of next 1/52nd piece that we are adding to. And so we would expect this value to increase some amount. And we could certainly try that. This would be 1,000 times 1 plus 0.03 divided, in this case, into 50 seconds. So very, very small. 50. Seconds to the power of 52 times 10. And plugging that into my calculator, I get that this is, again, rounding to the nearest 2, 1349.74. Okay, so it didn't increase us by that much, but we do see a little bit more money here, right? Doing this weekly, doing this 52 times per year, does in fact net us a little bit more money than if we were to do this every 3 months. All right, so you guys are walking into a bank, and you're setting up a new account. You're trying to figure out kind of what interest rate to go with, and the bank teller's feeling very, very nice. They say, we are going to charge you, we're going to give you 3% interest on your account, and you get to pick the number of times that gets updated. So you could spread that out across, like you could do it twice a year, you could do it 10 times a year, you could do it once every 2 years. What would be in your advantage? What kind of number would you pick, the number of times per year that you're going to be kind of updating this account, if you wanted to maximize the amount of money that you were trying to make? Okay, so 365 certainly wouldn't be bad. That would be like once a day your account's getting updated. Could we do better than once a day? Yeah, we could do twice a day, right? Maybe we're doing it like, I don't know, what would that be, like 730 times over the course of the year? That would certainly be really good. Can we do better than that? Yeah, realistically, we want it to be all the time, right? We would want it to be every single nanosecond of every single nanosecond. We are getting our account updated. If we had to give this as a number to the teller, maybe not a number, but kind of like a stand-in for a number, we'd say infinity, We would like this to be done an infinite number of times per year so that we are maximizing our count. Now, in terms of like practicality, to Haddon's point, as soon as you get beyond like 365 compoundings, what you're affecting are like the beyond those first two decimal places. And so yes, technically you are getting you're getting more bang for your buck, but it's so small that you don't really see it. So like 365 is actually generally kind of a good benchmark for it. Other fun fact is that interest rates that the banks take away from you so that they charge you generally do compound like this, and the ones that they give you generally don't. So a 3% interest rate that you are being charged will cost you more money than a 3% interest rate that you are getting added to your account. Fun fact. Okay, so ideally we would like to do this an infinite number of times. Now we can't just go plugging infinity into our function. Infinity is not a number. We need to apply a little bit of calculus in order to kind of get around this. Nothing that we haven't actually already done in this course. We're not going to talk about it in terms of the calculus, but rather than plugging infinity in, we're going to just talk about the idea of what happens as x goes to infinity. What happens as x gets really, really, really big is the number of times we are compounding. We do it every second, we do it every nanosecond, we do it every instant that exists. What happens as that breakdown gets smaller and smaller and smaller? Now the principle in this case, that initial amount isn't really going to affect anything. It'll be acted on, but as our value of x changes, that's not really going to affect much. And in fact, maybe a better way to do this would be to write this as n goes to infinity, because that's kind of really the number that we're affecting here, right? The number of compoundings. And in particular, the rate as well, also not something that's going to be super, super relevant. We're going to focus on just kind of the bare bones. What happens to this object here? 1 plus 1 over n to the power of n. This is kind of like if we strip away a lot of the detail of this formula right here. We're ignoring the time, we're ignoring the value of r. What is kind of going on as we just focus on the compoundings and what the compoundings are doing? All right, two different things that are happening here mathematically as x gets really, really, really big. First thing I would like to observe is that this base is always greater than 1. And we have an exponent that's getting large. A base that's greater than 1 raised to a very, very large power is going to do what? It's going to increase. It's going to get really, really big, presumably. But something else is happening to our base as our exponent is getting really, really large. What is happening in particular to this 1 over n piece as n gets huge? It's approaching 0. And so our base is approaching what value? One plus something that's approaching 0 is going to approach 1. It's going to get closer and closer and closer to 1. And 1 raised to a really, really large value is going to do what? It's just going to stay 1. Right? 1 raised to anything is just 1. That's approaching that base that's super boring that we don't really want to care about. And so we have this fight here. Our exponent is trying to drag us towards infinity, and our base is trying to settle down at 1. Where does this balance? Who wins out? Does this n that's in the exponent kind of take over and drive us towards infinity, or do we see some kind of meeting in the middle? This actually is a value that converges. This is a number. In particular, the number that this settles down on is about, I always get the decimals mixed up with this one, 2.71828, so on and so forth. A little less than 30. Right? Remarkably, this number shows up a lot, not just in exponential functions, exponential models, although it very naturally shows up in exponential models. It shows up a lot when you look at complex numbers. It shows up a lot when you do statistics. It shows up in so many different facets of math that are seemingly entirely unrelated to each other. So much so that this number has a very special name. We call this number E. Right, this is objectively the best number that exists, is this value of E right here. There's so much that you can do with it. Euler's formula is a really cool one, where if you take e to the pi I, that this is actually equal to -1. So taking e, raising it to an imaginary power, somehow turning it into this negative number here. This is an idea that we might explore a little bit when we take our more refined look at complex numbers. But for now, just kind of a little fun fact there. And so we get this convergence. Most of our function settles down on this value of e. And so if we are compounding infinitely, or what we might say instead, if we are compounding continuously throughout the entire stretch of time that we are given, we can rewrite our formula here. Rather than using this 1 plus r over n, where n is going to infinity, we are instead going to say that this is equal to p times e to the rt, very famously known as the PERT equation. This is our continuous model for our growth here. Remarkably, this doesn't just apply to compoundings, or in particular, doesn't apply just to finance. The PERT equation is very specifically economics. We're talking about principal, we're talking about amount. That's cool and all. But often how you might see this is we could, for instance, take our original exponential growth and decay model and say, okay, let's say I want to look at continuous exponential growth, continuous exponential decay. Again, that 1 plus r can be rewritten, and we would get that this is going to be a times e to the rx. I mean, this is just like our continuous model for exponential growth. This or decay. It's the exact same thing, right? In the same idea that the compound interest formula is just one application of our exponential growth or decay model, this is just one application of our continuous exponential growth or continuous exponential decay. And this actually does a better job of modeling than a lot of kind of the situations that we'll look at. We'll see in particular, when we're talking about radioactive decay, technically speaking, radioactive decay is a discrete event. There is a single ion that is breaking apart into, or a single isotope that is breaking apart into pieces. But it's happening so frequently, and there are so many that are doing it at once, that really it makes more sense to model it as if it is continuous. Same with, say, like the growth of massive populations. Like if I was looking at the population of humans and wanted to find a growth model that worked well for that, then it would make a lot more sense to use continuous growth rather than kind of like an instantaneous growth or a discrete growth, not because a human birth is like a continuous event, but because instead it's so many discrete events happening at once that it might as well be continuous, right? Like if a child is being born once per second, then we might as well use the continuous model rather than trying to break apart what that percentage is going to be spread out over the course of a year. All right, so let's tackle C now with our new formula here. Exact same situation, still looking at 3% a year, but now we are maximizing our account. Now we are saying, okay, rather than compounding 52 times a year, I'm going to compound an infinite number of times a year, and that's going to get me the most money possible. That should maximize my account here. And so we're still starting with that same 1,000. And now we are looking at e to the, what is our value of r here? Well, that is still 0.03. And how long are we doing this? We are doing this over 10 years. And so what do I end up with? Plug this into your calculator. I get 1349.8, like 6 or something. Yeah. And so we have successfully, by doing this an infinite number of times, saved 12 cents. Or made an extra 12 cents. Okay, so 52 times a year was actually pretty good. Doing it weekly was pretty good. 365 would have pretty much been perfectly sufficient. We really wouldn't have seen much of a change, but we can be very confident in saying that this is the most amount of money that we could possibly be making with this initial value with this particular interest rate. All right, and again, this is an idea that can be applied not just to money, but also to every other exponential growth, every other exponential decay model that we have done. We looked at this fox population earlier, where the growth was happening by 13% a year. If my claim is that this is a continuous growth, if this is happening all throughout the year, that 13%, which realistically it's probably not, but if that were my claim, then I could set this up as 237 times e to the 0.13 times, in this case, 15, and we would, instead of our 1482 foxes, we would get 1666 foxes. Okay, now, which of these are we more likely to see? Honestly, it's probably somewhere in between. Our population here is relatively small, and so we wouldn't expect this to be fully continuous. You're not going to see a fox born every second. You're not going to see a fox born every minute. And so this continuous model is probably a little bit overkill, but the true value probably lives somewhere in between these two, where it would be broken up a little bit more than just a flat 13%, but not broken up continuously, where it's, constantly growing, where it's constantly in this state of change. But kind of like we said, radioactive decay probably would be closer modeled to continuous. So again, kind of the better way here, starting with 1,000. And we're taking e to the, in this case, our decay rate, negative 0.024 times. We looked at what's going on after a week, so times 7. And this works itself out to be 845.35 kilograms. Yes.
So you got 52 for the weekly for 10 years, right? Because there's 52 weeks in a year.
52 weeks in a year, exactly.
How come quarterly is just 4? Wouldn't it be like a...
So quarterly means 4 times a year.
All right.
Yeah. So quarterly is 4 times a year. Semi-annually would be twice a year, and then biannually would be once every 2 years. Yeah. Good question. Yes, quarterly 4 times a year, and then weekly 52 times a year. I could do monthly, it would be 12 times a year. So. Interesting thing to note here. If we're talking about optimization, notice that our continuous model for decay also gave us a maximum, which I think is maybe a little bit unexpected. We would maybe expect growth to maximize and decay to minimize, but no, both actually maximize. If I am decaying by 20% a day, and I break that up into 4 or 5% decays, then my first 5% is going to be acting on a large number. My second 5% is going to be acting on a slightly smaller number. My third 5% acting on an even smaller number. My fourth 5% even smaller. And so the decay, the amount that I am losing, is decreasing as we go. And so to that end, we end up with a larger amount of stuff left because the amount of stuff lost is smaller. In both cases, you end up with maximums. You end up with continuous giving you kind of that upper limit for what you would expect to see. Okay, so we now have two different models, really two different formulas, right? We've got one that's like e to the r times x. We've got one that's 1 plus r to the power of x. How do I know on a quiz or a test or a Pearson, how do I know which one to use? Sometimes, I mean, realistically, I will tell you the one that you are supposed to use. So if I use the buzzword continuous, e to the r, whatever. If I don't want you to use continuous, I will probably either tell you to assume that it is non-continuous, so don't use e to the whatever, or I will say using the like a times 1 plus r to the power of x, find so on, right? But either way, I'm not going to make it ambiguous, and if it is ambiguous, then you could use either one, and I will give you credit either. But it should be very clear. Like, for instance, in a case like this, it's very clear that I'm asking you not to use continuous. I'm asking you to do it 5% over 4 times. And so I'm kind of adjusting your formula for that. All right, questions here with our growth and decay? One more thing that I want to look at, this is really just something that I kind of wanted you guys to see. We're going to talk about change of base a little bit later into the unit. That's going to be something that we have to do in when we are actually solving some of these exponential equations. So we'll talk about how we can adjust the bases of our exponentials. But I just kind of want to take a look at what some of that is going to look like, and kind of why we're able to do that. Really, the message that I have here is that it's very, very easy to kind of think of like 2 to the power of x as like one kind of parent function, 5 to the power of x as another parent function. But you'll often hear like math professors say there is only one exponential base that matters, and it's e. And we'll kind of see that when we work a little bit with logarithms, that we really only care about what's going on with e to the x, not for our class, but pretty much for every other class. And that's because these two bases can be changed to be whatever it wants to. I could write 2 to the power of x as 10 to a power, or 7 to a power, or something like that. It might take a little bit of work, but I certainly could do that. And so looking at these two graphs, one of these is 2 to the power of x. One of them is 5 to the power of x. Which one is going to be which? Which one is the red? Which one is the green here? Yeah, so what's the logic with this? Yeah, so notice here that our red curve reaches larger values of y faster than our green curve, right? The basic shape of the two is the same, but for smaller values of x, for instance, think about plugging like something small like 2 into x. This would be 25, this would be 4. We reach larger values of y faster with the red. What was the transformation that we talked about way back in Unit 1 that adjusted the speed at which we reach certain values of y? For instance, it was like the difference between... Yeah, exactly. That is our stretch or a compression. And we said it's a little bit tricky to tell is what we're looking at like a vertical stretch or a horizontal compression or vice versa, because oftentimes they have very, very similar effects. So I'm not going to make a claim as to which one is which. We're just going to kind of leave it at that what we are seeing here is not a different function. It's not different behavior. What it is a transformed version. One of them is being stretched or compressed in some direction. All right, so this is either being probably like a vertical stretch or a horizontal compression, depending on, I guess, what we're assuming is our base function. If we're thinking about how we go from 2 to the x to 5 to the x, we're either compressing it or stretching it forward. All right, so one of those two, maybe even both. Maybe there's a way to write it out as both. But one of those two should be happening to what we see here. All right. The other thing I wanted to look at was the difference between a base that is greater than 1 and a base that is between 0 and 1. All right. This is often given to you in books as like exponential growth versus exponential decay. Like you'll often be told to just like, you just need to memorize. When the base is greater than 1, we've got a growth model and it's going like this. And when it's less than 1, we've got a decay model and it goes like this. What are these graphs of each other? What does this really look like? What transformation do we see here? This is a reflection. What kind of reflection do we see? About the y-axis, which is a horizontal reflection. All right, so we're reflecting about the y-axis. Notice that our x values have really just kind of flip-flopped. And so sure, we could think of these as like two separate models, but again, my claim is that growth and decay are really the same thing. They're two sides of the same coin. And in fact, that is exactly true. 2 to the x and 1/2 to the x are just reflections of one another. Normally, how do we do horizontal reflections? Well, we take x and we make it negative. And in fact, when we look at what 2 to the negative x is, it is exactly the same as 1/2 x. It's hard to see what's going on, but notice that purple line is being perfectly overlapped by this black line. All right. And so this base being less than 1 is really not a change in our function. Again, there's not really a difference between a growth function or a decay function. A decay function is just a reflection of a growth function, of a growth model. Right? And so you can always take this base and rewrite it. In this case, you could take 1/2 and rewrite it as 2 to the negative 1. And then we would see, okay, yes, in fact, when we are comparing 2 to the x versus 2 to the negative x, that is our reflection. And so some of these transformations are a little bit tricky. They kind of hide inside the bases, but we can really kind of pick them apart when we are rewriting what we have in terms of different bases, which is kind of nice. Just some transformation ideas that I wanted you to be a little bit familiar with. Just this idea that, yeah, this whole growth versus decay thing, they're really just the same. Questions with anything from exponentials? Any questions from our intro to exponential functions? How are you feeling? Pretty good, pretty sleepy. I see I've lost 3 of us. All right. Got about 30 minutes left. So there's the 3-1-3-3 cluster, a couple of those kind of last ones looking at some of the exponential or the compounded interest types of questions. The 1 through 7 on the 3-1-3-3 classwork due at the start of class tomorrow for that extra credit point. We're going to start looking at probably something a little bit new, exponential functions, stuff that we've looked at before in various algebra classes. Logarithms might be kind of the flip side of that. That's a little bit new for us. But we'll take a look at that. It's not too bad. And we'll do that tomorrow. Also keeping in mind, we've got the deadlines for the 2.6, 2.7 classwork, as well as the Unit 2 study guide coming up. So those final deadlines deadlines, making sure that we are working on getting those in as well. Got 30 minutes left. You guys have the rest of this class to work on whatever you need to be working on. And of course, if you have any questions for me, more than welcome to